Hi there, and welcome to our Mech 447 project. Today we'll be talking about carbon capture and negative emission technologies. So let's start by looking at why negative emissions are important. This graph shows projections over the next 80 years and demonstrates that without change, atmospheric CO2 concentrations will rise to dangerous levels, causing large-scale global warming. Evidence shows that without decreasing emissions, global temperatures will likely reach 1.5 degrees C above pre-industrial levels by the year 2040. It is now known that decreasing emissions is not enough. According to the IPCC, negative emission technologies play a large role in limiting warming to 1.5 degrees C. Between 100 and 1,000 gigatons of carbon dioxide will need to be captured in total. Some industries are relatively easy to decarbonize. However, there are a handful of very tough to near impossible industries to fully decarbonize. Industries such as aviation, steel and cement production, and load-following electricity generation. To negate these types of emissions, roughly 10 gigatons of carbon dioxide will need to be captured yearly. The four negative emission technologies we'll cover today include afforestation, BECCS, enhanced weathering, and DAC technology.
Forest ecosystems have potential as NETs. Human interaction with forest has historically been deforestation and subsequent land use change, which causes carbon emissions and removes uptake potential. This can be reversed with either reforestation of logged areas or afforestation of areas which have not been forested for at least 50 years. Carbon uptake is increased by selecting location for growth rate. Tropical forests grow faster than temperate, and by sustainably harvesting to maintain that growth rate. Maximum sequestration is obtained when the lumber is used in projects with long life cycles. Planting a forest will reduce the local albedo of the area. This is also mitigated by a tropical location with more cloud cover. Forests are susceptible to disturbances, such as drought, pests, and fire. As an NET, afforestation requires a large area. However, restoring the forest results in cultural, social, and environmental benefits.
Trees from afforestation can be used in the next NETS technology, BECCS, or Bioenergy Carbon Capture and Storage. BECCS substitutes the fossil fuels used in standard combustion power plants for biofuels such as trees. The emissions from this, already cleaner fuel source, are then stored in reservoirs beneath the ground using current carbon capture and sequester technologies. BECCS benefits are that it's easy to convert current power plants to BECCS power plants. It's scalable and versatile. Its drawbacks are that it's deeply layered, making it possibly not negative emissive. The land area requirement could be as large as 2 times the surface area of India, and it would likely displace already in place carbon sinks, such as current farmland.
Oftentimes we look to nature for our ideas. Enhanced weathering is based off the naturally occurring chemical weathering process. Carbon dioxide present in the atmosphere reacts with organic silicates to naturally sequester carbon. In nature, this could take years to occur, so the idea of enhanced weathering involves accelerating this process. The basic idea consists of mining olivine, which is a widely available silicate-containing mineral that easily reacts with CO2, and processing it into a fine powder to decrease reaction time. The olivine powder is then spread over the land or dissolved in the ocean to begin the CO2 sequestering reaction. So how much olivine is needed? Well, 1 ton of olivine is capable of removing 0.8 tons of CO2. That results in a grand total of 12.5 gigatons of olivine needed. That's equivalent to approximately 833 million school buses. The good thing about this technology is that it's naturally occurring and has the potential to remove large amounts of CO2 from the atmosphere. The bad includes the increase in mining and industrial activity required to obtain such large amounts of olivine. Also, adding that much olivine to our environment has unknown side effects to our ecosystems.
DAC technology uses chemical sorbents to bind to CO2 and remove it from the atmosphere. These plants produce high purity streams of CO2 which can be either utilized, such as creating synthetic fuels, or it can be permanently stored underground in things such as salt aquifers or depleted oil reservoirs. The benefits include that its operation is independent of its location, meaning it has the same effect no matter where it is placed in the world. It is also scalable to capture large amounts of CO2, limited only by the storage capacity. Some of the drawbacks of the technology are its high capital costs and large energy demand. To give a scale of the energy demand, capturing 10 gigatons per year would require the construction of roughly 12 billion onshore wind turbines, providing enough power for 28 trillion homes, 2.3 million times the number of homes in Canada. Large efforts are being made to reduce the energy demand, reduce the costs, utilize waste heat resources, and increase overall efficiency. To summarize the four technologies discussed, the anticipated cost, potential scale, and energy requirements are shown in this table. Afforestation shows the lowest cost, while direct air capture shows the largest scalability. It is clear there are trade-offs associated with each, there's a large amount of variability, and more research needs to be completed in order to determine an optimal portfolio of solutions.